All right, so today we have Max Hübner tell us about 0-1 form and two-group symmetries with boundary geometries. Take it away.
Yes, thanks for the introduction, Julius. And well, thank you for inviting me here to talk and present my work at the Quiver Meeting. So as you just said, I want to tell you today about 0 form, 1 form, and two-group symmetries in the context of geometric engineering. And so in particular, I'll be talking about these two papers here, which appeared in February, and the first of which was written in collaboration with David Morrison, Sakura Schäfer-Namiki, and Yinan Wang. And the second was written in collaboration with Miriam Svetic, Jonathan Heckman, and Ethan Torres. So let me motivate this talk with some semantics and by recalling the ideas of geometric engineering. So many years ago, it was realized that supersymmetric quantum field theories can be studied by embedding them as localized degrees of freedoms into string theory, typically localized on branes or at singularities. And in the process, the field theory is parameterized by geometry. The next step then is usually to manipulate the string theory setup, for example, via some dualities, and then project back down onto the field theory sector. If this is all done intelligently, one uncovers relations between the field theories which are far from obvious when looking at the field theories themselves. Now, crucial to this whole set of ideas is, of course, the Geometric Engineering Dictionary, which tells us how exactly the field theory is parameterized by geometry. So on the geometry side of this dictionary, everything is organized by geometric structures. So on the first page of the dictionary, we might have some topology. On the second page, there might be some differential geometry. On the third page, Riemannian, and so on. And so mapping this data across the dictionary, we expect that our physical data is filtered by these geometric structures. And in particular, there's a conservation of difficulty. So topological structures in the field theory should correspond to topological structures in the geometry. Now, it's been, I think, 8 years since Gaiotto, Kapustin, Sabeck, and Willett wrote their paper on generalized global symmetries. And the main takeaway from that paper is that we should think of symmetries as a collection of topological defects. And so whenever the theory is geometrically engineered, the data of these topological defects should be encoded in the topology of the engineering geometry. And this correspondence is exactly going to be the focus of the talk today. So we're going to have a look at higher symmetries in field theories and topological structures in geometry. So we're by far not the first people to have thought along these lines. There has been work on this correspondence for 60.1,0, 62.0 theories, for 5D gauge theories engineered in M theory on isolated hypersurface singularities. And there's been work on class S setups and their type 2B geometric duals, and so on and so forth. And in particular, some of the ideas I'm presenting today have been also independently backed up by this recent paper here by Michele Iñaki and Sakura. So let me be a bit more precise now.
Can I ask a small question?
Go ahead.
About the first sentence. Is there a deep meaning to this line that you wrote, this kind of exact sequence, where string theory is between two SQFTs, or is it just some symbolic?
It was meant poetically.
Okay, there's no. Okay, thank you.
We'll have vibrations and embeddings and projection throughout this talk, so it
sure
seems to be the overall theme.
Okay.
Okay, so right in this presentation, so we're always going to be geometrically engineering in M theory. So the setup will always be M theory plus some singular space. And depending on the space, we're going to engineer a 7-dimensional or a 5-dimensional or a 4-dimensional theory. And the topological data we're going to be interested in of the singular geometry is the topology of its boundary. And we're going to set this in correspondence with the 0 form, the 1 form, and the two-group symmetries of the field theory. So here's a sketch of the generic geometry we'll be considering. So we're going to have some non-compact space X. It's going to have a boundary, partial X. and it's going to have singular loci, which are marked here in red. These singular loci come in compact and in non-compact forms. So the compact singular loci are going to support the field theory degrees of freedom, and the non-compact singular loci are akin to flavor brains and are going to be relevant. Geometries which take this form are example elliptically fibered Calabi-Yau threefolds, some toric quotients of C3 or G2 spaces, although I will not have a lot to say about the latter in this talk. Okay, so now having discussed this introduction, let me tell you how the rest of the talk is going to be structured. So first, in the second part, I'm going to recall a few basic definitions, defect groups, higher symmetries, and how these things relate. And we're going to look very explicitly at a simple example, which is relevant for all more complicated situations to follow. Then, once we've understood higher symmetries, and in particular one-form symmetries, we're going to return to ordinary zero-form global symmetries and ask how we can determine their global form from geometry. Once one-form and zero-form symmetries are understood, we'll discuss two groups, which are a mixing of the two. And then I'll conclude, tell you what I didn't tell you about, and give an outlook. Okay, so first I want to talk a bit about the defect group of a field theory in d dimensions. So the defect group is basically a collection of mutually non-local defects. They're organized by their dimensionality P. The defects we're considering are going to be topological and invertible. And in particular, the latter implies that their fusion algebra is that of a group. So we indeed get a defect group. Mutual non-locality between two defects means that there is a phase ambiguity in correlation functions when these are inserted. So for example, consider the insertion of a p-dimensional defect and a d minus p minus 2-dimensional defect. And then as one moves one around the other, returning to the original configuration, the correlation function can pick up a phase alpha. And this phase alpha is determined by a pairing on the defect group. And whenever this phase alpha is non-zero, the defects are not mutually local. Now, this is a problem for the theory. It's not well defined if these phase ambiguities persist. And so to get a well-defined so-called absolute theory, one needs to restrict the spectrum of admissible defects to, well, a subset of a maximal subset of mutually local defects. And these subsets are referred to as polarizations, and every polarization determines an absolute theory. Now, because choosing a polarization basically fixes the extended operator content of your theory, it also fixes the symmetries acting on these extended objects. And so it turns out that the higher symmetries are simply the Pontryagin dual of these polarizations. Okay, so what does geometric engineering bring to the table? So let's assume that our theory has been geometrically engineered in M-theory on the space X. In this case, we should think about the defects we just discussed as infinitely heavy probes, extended probes. And p-dimensional probes now split into two contributions, depending on whether they were constructed using M2 branes or M5 branes. And the way to construct these probes is by wrapping M2 and M5 branes on relative cycles, or equivalently non-compact cycles. And with this method, we get following characterization of these two contributions to the defect group. So here, this numerator contains the relative homology group of the engineering space with respect to its boundary. And so this contains all compact cycles, and in addition, cycles whose boundary lie on the boundary of the engineering space. So these are cycles which stretch all the way to infinity. Now, there's a nice long exact sequence in relative homology for this pair, and this allows us to rewrite this quotient as, first of all, homology groups purely of the boundary in 1 degree lower. And here we need to restrict to cycles which trivialize when one includes them from the boundary into the bulk. And this characterization over here is very intuitive. So, for example, consider we have a one cycle in the boundary, which trivializes when included into the bulk. This means that somewhere in the geometry there exists a point where I can shrink this one cycle. And so starting from there, I could have alternatively fibered it radially outwards and constructed a cigar-like thing. And it's these kind of non-compact cycles that we wrap M2 branes and also M5 branes on. So right, this engineers these two contributions to the defect group. Another nice thing about the geometric setup is now that the pairing on defects has been geometrized. And the pairing between defects is the linking pairing in the boundary between the associated cycles here. Okay, so now we've discussed it from the field theory point of view and a bit more geometrically. So let's make things very explicit considering an example. And the example I want to consider is M theory placed on a local K3 surface. This is going to engineer some 7-dimensional theory. And so let's characterize that. So the starting point is going to be this elliptically fibered K3 surface. It's elliptically fibered over the complex plane. And we're going to admit a single singularity of Kodaira type phi, which sits at the marked point Z. So here I've sketched the geometry. There's the base copy of C. There's a marked point where the fiber degenerates, and there's a generic elliptic fiber. Now, according to the previous slide, we need to understand all these cigar-like objects. And in particular, we need to understand the homology of the boundary of the space. The boundary of this local K3 is, well, it's the elliptic fiber restricted to the boundary of the base, which is just a circle. And this structure allows us to compute the homology groups very, very easily. So there exists this short exact sequence, which computes for us the homology groups of the boundary, given the monodromy data on the fiber. And this sequence is also very intuitive. So for example, for every monodromy invariant n-1 cycle, I can multiply that with a circle, and I'm going to get an n cycle. And then this part, this contribution here, is understood as taking the n cycles in the fiber, and then one needs to quotient out by some extra boundaries which arise due to monodromy. But okay, the main story, or the main takeaway is that we can compute these things quite easily. And so this quotient, or this becomes this co-kernel. And so we find that in most cases, there is a single cigar-like non-compact 2-cycle in geometry. And so the defect group of 1 extended objects and 4 extended objects in the field theory, constructed by wrapping M2 and M5 branes on this cigar, is, well, a copy of this homology group. So far we would say that we've engineered a relative 70 super Young-Mills theory with gauge algebra determined by the Kodaira singularity, and the defect group of the theory are M2 branes and M5 branes wrapped on this cigar. Now that we've determined the defect group, we need to determine the maximally mutually local subgroups. And so to do this, we're going to resolve the Kodaira singularity. And this introduces some exceptional curves, C alpha I. And these intersect according to the Dinkin diagram of the Lie algebra associated with the elliptic singularity. Now, there is a very nice trick that we can play to analyze whether the defects that we just discussed are mutually local or not. And we need to study these cycles. And so what we're going to do is we're going to dualize to linear forms via the intersection pairing. So we're going to take compact 2 cycles and we're going to insert them into the intersection pairing and generate a linear form like this. And similarly, we're going to do this with relative 2 cycles. Because this here is a subgroup of this, we find that the images are nested like this. And so what this identification allows to do for us, it allows for us to find a compact representative for a non-compact cycle. And this compact representative is going to be a rational combination of compact curves. And its distinguished property is that it intersects all compact curves in the same way that the non-compact cycle does. And so we find a compact representative in here. So as an example, I've brought along the compact representatives for IN, so SU, and I star, so 2n minus 3, SO, fibers. So here are the Dinkin diagrams. This is SO for n plus 2. And here are these cigar-like objects extended in terms of compact cycles. And the nice thing is that now with basic intersection theory, we can compute the self-intersection of these non-compact cycles. And this is going to be exactly the same thing as the linking pairing of the boundary of these cycles in the boundary. So I'm going to be talking a bit more about this in Freiburg at the Simons meeting on the 8th of June. So there's a lot one can do with these compact representatives. But the main takeaway for us is simply that, right, the boundary of these cigars link non-trivially, or equivalently, this self-intersection is not zero. And so the defects we've constructed by wrapping M2 branes on these cigars and wrapping M5 branes on these cigars are generically not mutually local. So we need to pick a mutually local subset. And so the polarization we're going to pick is the one given by, it's called the electric polarizations. We keep all defects which are constructed from M2 branes and throw away all M5 brane defects. And this is the polarization we're going to stick throughout this talk. Once we've made this choice, we say that, well, the gauge group is then chosen to be the simply connected one, and the Lie algebra, well, with this Lie algebra. So we end up with the result that we've engineered 7-dimensional super Young-Mills theory with gauge group G phi. The extended operators are the Wilson lines, constructed from M2 branes, and they're acted on by the one-form symmetry, which is the center of this simply connected Lie group. And the point is that this example basically captures everything one needs to know for the geometric engineering of higher symmetries. One always needs to ask what are the non-compact cycles, similar to the cigars in the geometry. One then needs to have a look at the boundaries of these cycles in the boundary of the engineering space, ask, well, how do they link? And this then allows you to choose a polarization. And this completely fixes what are the higher form symmetries of the theory you've engineered. Okay, so now we've in length discussed these higher symmetries, and now I want to turn to the zero form flavor symmetries. And the question here is going to be, what is the global form of these flavor symmetries? And maybe the question before that is, when do we even expect flavor symmetries to be present in a geometric engineering context? And so the conservative answer is that we expect flavor symmetries to be present whenever we have flavor branes. And when everything is geometry, flavor branes take the form of non-compact ADE loci in the geometry. So the generic geometric setup that we find ourselves in is the following. We have our non-compact space X. It has a boundary, partial X, and there are non-compact ADE loci extending all the way to infinity, all the way to the boundary. And they are labeled by, well, Lie groups, Lie algebras, G1, G2, G3. And now the naive guess for the non-abelian flavor symmetry is that, okay, we know the algebras, so let's just write down the simply connected Lie groups for all of these flavor branes. And so this gives us the naive flavor symmetry. Now, this originates from looking at all of these singularities locally separately, and it's a bit too quick because all these singular loci live in the same boundary geometry. So the point I'm going to make now is that there can be some global interplay between these singularities which corrects this naive guess. And the way we're going to argue is exactly the same way we argued for the one-form symmetries in the previous example. Namely, the way that worked is we right? So before we asked what are the gauge-Wilson lines, and then because the one-form symmetry acted on the gauge-Wilson lines, we basically knew the one-form symmetry once we had characterized the lines. And so we're going to play the same game. We're going to find out what are the flavor-Wilson lines, and this is going to fix the global form of the flavor symmetry. Now, in geometry, right, the gauge-Wilson lines, they were associated with these non-compact two cycles in X, these cigar-like objects. And in particular, right, they were fibered by one cycles which vanish in the bulk. Now, flavor-Wilson lines are going to correspond to compact two cycles in the boundary, and they're going to be also fibered by vanishing cycles. And in this sense, they are very similar objects. So to make this a bit more precise and to permit computation later on, let me introduce a few objects. So first, I want to define K as the ADE locus in the boundary. It has irreducible components Ki. I also want to define the tubular neighborhoods of these ADE loci in the boundary. And these are, well, they're a disconnected sum of the tubular neighborhoods of all the irreducible components. And I also want to define the smooth boundary, which is the boundary without the singularities, simply just removed. And then of interest will also be this intersection here. So this can be thought of as all the local boundaries to the ADE singularities. So I'm intersecting the tubular neighborhood with the smooth boundary. And generically, right, this takes the form of the boundary of the ADE singularity fibered over the singular locus. So here's a small comic which is supposed to capture some of these things. So we have our space X, it's all of it. We have a non-compact ADE locus. It intersects the boundary in a circle, which is the Ki. And then there's this ribbon around it, which is the tubular neighborhood. And then you can think of these the boundaries of this ribbon as this intersection here. And all of it sits in the boundary of the engineering space. Now we can make our first geometric characterization, namely, where does the naive guess for the flavor symmetry come from? So it's a fact for ADE singularities that the torsional one cycles in the boundary for ADE singularities capture the center of the simply connected Lie group, whose Lie algebra is determined via gamma I. And so the naive flavor center symmetry is now geometrically characterized by this homology group here. We take all the local boundaries of all the ADE singularities and just, we sum over them. And so this is straightforward. But now I want to understand how in this geometric characterization, the generators of all of these groups interplay if they are part of the same global geometry. And the tool to analyze this mixing is the Meyer-Vietoris sequence. And the covering we're going to apply the Meyer-Vietoris sequence to is the covering of the boundary by, the smooth part, everything but the ADE singularities, and the local model for the ADE singularities, these tubular neighborhoods. So here I've written out the Meyer-Vietoris sequence in its general form. We have these local boundaries. They embed separately into the smooth space and the local models, and then these two patch together to the total space, which is the boundary in this case. And now we claim that the flavor Wilson lines, which are isomorphic to the center of the flavor symmetry, are characterized by these homology groups right here. So we can characterize them as the image, or then by exactness as a kernel. And each of these descriptions are equally illuminating, so let me put some words to them. So here we're considering the boundary map from two cycles to one cycles. So given a compact two cycle in the boundary, we're going to map them to one cycles, which are associated with the naive flavor center symmetry, so the torsional one cycles of each ADE singularity. And the way we do this is we basically intersect this compact 2 cycle with these local neighborhoods. And then, you know, this cuts out cross sections of the 2 cycle, which then is the image in here. Equally, we can start with these collections of torsional 1 cycles in the boundary and can ask what is the kernel when we embed it back into these 2 parts. And whatever, and the collection of cycles that is in the kernel means that, okay, once we put them back into the smooth boundary, because the trivial homology, we can, in some sense, fiber them to a common point and build a compact 2 cycle from them. And so these things are indeed equivalent. And the Wilson lines are now in correspondence with these objects here. So we have 2 cycles fibered by vanishing 1 cycles of the ADE singularities. Okay, I appreciate that this might be a bit abstract, but it becomes a lot clearer when we look at a specific example. So let's now look at 5DTN theory and discuss these structures. So 5DTN theory is engineered in M theory by this quotient of C3. So we're quotienting C3 by 2 copies of Zn. And each of these acts as written out here on the 3 coordinates of C3. We have an phase rotation, an ADE phase rotation by omega on the 1st and 3rd, and by eta on the 2nd and 3rd. And they're primitive nth roots of unity. So, and now we clearly see that this geometry has 3 planes of an-1 singularities. And these are located at wherever 2 coordinates vanish. So, for example, if Z1 and Z3 vanishes, then the action by omega folds an ADE singularity parameterized by Z2. If Z2 and Z3 vanish, we get an ADE singularity folded by eta parameterized by Z1. And when Z1 and Z2 vanish, there's a diagonal Zn in here, which folds an ADE singularity parameterized by Z3. So there are 3 ADE planes.
A question?
Yeah, go ahead, Ami.
What happens if you change the 2 values of the index of Z?
That's completely allowed, and it's going to. So we spelled out all possible cases in the paper. This one is, I thought, the physically most interesting one. It changes these. Okay, what happens is I get also 3 planes. One is going to be n, one is going to be whatever I change this to, and then the last plane is going to be the GCD of n and m.
Yeah. Okay. Thank you.
Okay, cool. Right, and so, okay, what do I say? I wanted to now say that this one doesn't have, this has trivial 1-form symmetry. And this was shown by a paper late last year and early this year. So now the naive guess for the flavor symmetry of this theory is, well, we know the algebra. We have 3 planes, so we have SUN cubed. And now I want to understand what is the global form. And for this, we need to understand what are the flavor Wilson lines. So it's convenient to now reparameterize the problem in terms of toric coordinates. So let me introduce them here. So we have the radii, pi. We have the arguments, theta i. And parameterizing C3 with respect to these, we represent C3 as a T3 fibration over this positive octant. The T3 fiber degenerates at the faces to a T2 fiber and at the edges to a circle fiber. Also, this gives us a very nice characterization of the boundary of C3, which is a 5 sphere, similarly in toric coordinates, and it's fibered by a T3 over this triangle here. And now the point is that because we have 3 planes, they intersect the boundary in 3 circles. And each of these 3 circles is located where 2 of the coordinates vanish. So they are located in the fibers, the circles, which project to P1, P2, and P3. And this information is enough to now determine the flavor symmetry of 5DTN theory. So the first thing to notice is that this T3 fibration is trivial because we're only describing C3. And okay, we applied the quotient, and this is the boundary geometry. It's T3 fibered over this triangle base. And for example, consider P1. There's an ADE singularity along the circle above this. And it's folded in the transverse directions, which are Z2 and Z3. And so the vanishing one cycle is the Hopf fiber of the ADE singularity transverse to the ADE locus. So in particular, we now get the following picture in the boundary geometry. There's the ADE singularity, where this one cycle gamma 1 pinches, and going outwards from it, we construct the cigar-like object, T1. And all of this happens 3 times at these 3 points. Now, because these 3 circles, these 3, right, you can just see it, it's anti-symmetric, they sum to 0 in homology. This means that we can glue these cigars into one compact 2-cycle sigma. And the Wilson lines, the flavor Wilson lines are constructed by wrapping M2 branes on this sigma. So this is enough information to completely solve what I laid out before. So we just saw that we have torsional 2 cycles of degree n in the boundary generated by this sigma. There is a diagonal embedding into the naive flavor center. And so the flavor symmetry must take this form. It's SUN cubed mod Zn squared, where this quotient is exactly such that the diagonal Zn in here survives. And this result was independently found by Laksha in a paper where he considers this compactified on a circle. Now, it should be mentioned that we're blind to accidental enhancements. So T3, which is the E6 Binahan-Nemeshansky theory, we would predict an SU3 cubed mod Z3 squared. While this is compatible with enhancement of the flavor symmetry to E6 mod Z3, it does not predict it. So now I want to also discuss a second example, which is going to be relevant when we talk about 2 groups. And this is the example of conformal matter. So the geometry is now going to be an elliptic fibration over C2. And we place ADE singulars, or we place the elliptic singularities of Kodaira type phi L and phi right along transversely intersecting planes. The boundary of this space is now elliptically fibered over an S3, and it's going to be convenient to think about this S3 as itself fibered over an interval. And this is because each of these planes intersects the boundary in a circle. And we can think of these circles as the circles projecting to 0 and to 1 in this fibration of the 3-sphere base. So the boundary geometry, right, as I said, elliptic fibration over S3, and there are 2 Hopf links of discriminants in the boundary. So now we need to characterize again just the spectrum of 2 cycles, and we're going to do this by studying the smooth boundary. And so this is the space obtained by excising the singular fibers. And because we've excised the singular fibers, we've cut away the 0 and the 1 in the fibration before. And so this space deformation retracts to a fibration over S1 left and S1 right. So we have a space fibered over circles. We can again use this short exact sequence to determine its homology groups. And what we end up with is that the homology groups are determined by the monodromies about each of these elliptic loci. And here it's this Z2 are the 1 cycles of the elliptic fiber, and we're modding out by the image of these 2 monodromy matrices. And this object is very naturally understood to correspond to flavor Wilson lines. And this is because of what I tried to draw in the comic down here. So the situation we're in now is that, okay, we have the Hopf-Link, which are two disconnected discriminant components. We've now excised neighborhoods of these. And I'm claiming that these cycles here characterize one cycles which collapse at both of the discriminant components. So whenever I have such one cycles, I can fiber them from one discriminant component to the other. And this gives me this compact 2 cycle up here in the fiber. Now that I've excised these local neighborhoods, I've also cut open this 2 cycle, and all that remains of it is this equatorial 1 cycle, which is exactly the one captured by H1 partial X circ. Okay, so we're pressing on in our computation for example, SUN times SUM conformal matter, which is bifundamental matter. We find the flavor symmetry to be equal to this. And this is simply SUN times SUM modulo the GCD of N and M, which is exactly the subgroup of the centers which doesn't act on the bifundamental hypermultiplet. And so this is very expected. There's of course a more general version if I take different ADE singularities in this example. And in the paper, we also cover all A-type bases in more general elliptic models. Okay, so now we've characterized one-form symmetries, zero-form symmetries, and let's talk about two-group symmetries. So two-group symmetries arise whenever the topological symmetry defects of the zero-form symmetry act on the one-form symmetry defects. And in particular, the two-group quantifies the obstruction to turning on background fields for the zero and one-form symmetry independently. For the purpose of this talk, the two-group is going to take the form of two short exact sequences, written out here, and the Postnikov class. The Postnikov class is, I'm not going to have too much to say about it from a geometric point of view. It's standard. It's the Boxstein of an extension class of one of these sequences. Okay, but we will focus now on geometrizing these two short exact sequences. So what are the players in this sequence? We have the center flavor symmetry. We have the naive center flavor symmetry, and we have a leftover bit. So in a sense, we've geometrized this part completely. We have line operators modulo screening by local operators. These are the Wilson lines, which we've also understood. Then we have a slightly finer object, which are the line operators modulo screening by local operators transforming in representations of ZGF. And then we have the kernel of this projection, so also the leftover bit. So the last sequence is newer, so let's focus on that. Here I've written it out on the top line again. So let's first consider a simpler case. Let's consider an equivariant case. So let's assume that we're given, the geometry we're given is a global quotient of y by some finite group gamma. We now claim that this class of line operators is engineered by wrapping M2 branes on the equivariant one cycles of the boundary. And this is supported by the fact that we have this short exact sequence, where we project the equivariant one cycles onto one cycles in singular homology. And then there is a leftover kernel, which is, well, this space has singularities. So this leftover kernel can be viewed as a twisted sector. And so we make this identification here. This here are just the boundary one cycles, these cigar-like objects. So this is, we've already covered it. And then we have this twisted sector here left over. Now, in a more general case where we're not given the geometry as a global quotient, we should replace equivariant homology with orbifold homology, which replicates this locally. And then our claim is that this class of line operators are realized by wrapping M2 branes on orbifold one cycles. So here I've written out these short exact sequences, the field theory one and the geometry one, and this leftover piece we're going to call the twisted sector. Now, due to work by Thurston, Mortritz, and Pronk, we can characterize these orbifold homologies in the case of ADE singularities by following singular homology groups. So the first orbifold homology of the boundary is nothing but the singular homology group of the smooth boundary. Remember, and this is where we've simply excised the ADE locus. And the main observation now is that we've naturally encountered this object before, right, when we were studying the Maya-Vietoris sequence in earlier examples. So let's return to that. So the Maya-Vietoris sequence we're considering is, again, with respect to this covering. So we have the smooth boundary, and we have the local neighborhoods of the ADE loci, and it connected the homology groups like this. Now the point is that these tubular neighborhoods are very simple. They deformation retract to the ADE loci, which are essentially just a collection of circles, as we saw, for example, in the 5D examples. And here again is the comic of the various pieces of the appearing in the Maya-Vietoris sequence. Okay, so now we look at the sequence in degree 1, and we extract this this exact sequence from it. It truncates here due to connectiveness reasons. It truncates over here because we've manually just written the kernel here. So that's fine. And now we've encountered all of these pieces throughout this talk. This guy here was where the Wilson lines, the center symmetry, the one-form symmetry. This guy over here is the kernel, which characterized the flavor Wilson line. So this is the center of the flavor symmetry. This here was the naive, and was associated with the naive center flavor symmetry. And then we have this orbifold piece. And so one needs to remove a few free factors because these homology groups are trivial. And then these are the charged objects. And if we want to write the sequence with respect to the symmetry operators, which are the charge operators, we need to flip all the arrows. So what we've now achieved is that we've characterized the one-form symmetry, the center zero-form symmetry, geometrically by this sequence. It's now a general property of exact sequences that we can split them like this into two short exact sequences. And just using the geometric characterizations from the previous slide, we characterize these here geometrically as these short exact sequences. Now, renaming things, we could have made it a bit prettier, but the main point is that all of these groups are singular homology groups. We didn't need to resolve the singularities. We're just using topological data, and all the structures are encoded in basically one non-trivial map in each of the sequences.
Can you explain how you split the two sequences? How you construct the C? So the C is the thing that splits them.
Yeah.
Right. So how do you construct this?
Okay. I don't fully recall the details at the moment, but this is the point is here. Okay, so the point is that I'm not just cutting it in half. At the same time, I'm taking the Pontryagin dual. Exactly, and this is what fundamentally allows for the split.
So you're saying that each time you have an exact sequence with 4 terms, you can always find an object C which breaks it that way?
Yes.
Okay. Okay, thank you. And what's the interpretation then of the C?
So it's okay. It can be interpreted as in this case we're going to interpret it as the part of the naive flavor symmetry which is broken, which is not present. Okay. So Okay, so this is basically, this last sentence is what we've arrived at. We've computed the 0 form, 1 form, and 2 group symmetries from cutting and gluing constructions for orbit folds. Now, okay, another main point of this here is that it's actually rather computable. And so I want to end this talk with discussing an example. And this example is going to be spin 8 plus 2m gauge theory with 2m vectors in 5 dimensions. And so this gauge theory is engineered by this elliptic threefold. It's fibered over the base B, which is the total space of this line bundle. In most papers, you will find this geometry written out like this here. And this simply means that the discriminant locus takes following form. There is a compact P1, which supports the I star singularity, and there's a fiber class in this base, a non-compact curve, which supports the flavor locus, so the I non-split singularity. And I want to say a bit about what non-split means topologically. So here on the right-hand side, I've drawn this discriminant locus. And let's, for a moment, assume that we've resolved the singularity. And then we've introduced these exceptional curves. Whenever the singularity is non-split, that means that there exists a ramification point, that if I go around it, the resolved fiber is acted on by an auto-automorphism. And in particular, in this case, there is a one cycle which runs around these exceptional curves, and going around this ramification point, it's mapped to its negative. And as all things which are acted on by some sort of monodromy, it therefore needs to collapse at the point P. And so we can construct a cigar again using this cycle B. We fiber it from this point P all the way to infinity, and we get a non-compact 2 cycle. Okay, so this is the bulk geometry. Let's quickly talk about the boundary geometry. So the boundary of this elliptic threefold is, of course, elliptically fibered over the boundary of the base, which is this length space. And this is now all, okay, and the discriminant locus set on a fiber class, and so it's going to intersect the boundary along a hop fiber here. And this characterization is already enough to completely compute everything. So the torsional one cycles of the boundary turn out to be a copy of Z4 and Z2. The Z4 is the Hopf cycle in this space. The Z2 is the B cycle from the previous slide. To compute the homology groups of this smooth boundary, which is the orbifold homology, we excise the singular fibers. Right, the singular fiber was that's the discriminant locus in the base that removes a hop fiber from this S3 mod Z4. So in this fibration of the base, we've punctured the S2. Now the S2 with a point removed, deformation retracts to a point. And so the base with the discriminant locus removed, deformation retracts to a different hop fiber. And so the whole boundary, the smooth boundary, deformation retracts to a 3-manifold which is fibered over this Hopf fiber, S1H Hopf primed. And the topology of M3 and equivalently this guy is completely determined by the monodromy around S1H prime. Now, this Hopf cycle links both the original Hopf cycle, which supported the non-split singularity, and the bulk P1. And so it's acted on by both of these monodromy matrices, giving a total of this monodromy matrix. And this is then again enough to just compute the homology groups. They take this form for M even, this form for M odd, and there's a universal Z4 factor which comes from the base. And so now we can write out these sequences. So for odd M, we have it like here. Again, these two are mapped isomorphically onto each other, so we could cancel them if we wish to. And the main point here is that the second sequence does not split. And this characterizes that we have a non-trivial 2 group. For even M, the sequence in the bottom does split. Right. Also, these sequences are enough now to tell us what the flavor symmetry is of the theory. And in this case, it's SP2M modulo Z2. And this was also replicated in a paper last year. Okay, I think this.
Hi, Max. I have a question.
Yeah, go ahead, Yinan.
So in a formula, so on a slide before, so you show that the ZGF and the C check are the same thing, but here it's
CGF?
different.
Sorry, say again.
So on a slide before, so you identify the ZGF and all these groups with some homology groups, right?
Yeah. Sorry, sorry, am I on the correct slide? Sorry, which one are you?
No, before that. I think. Yeah, this one.
Yeah.
So this one, as you can see, so the groups for the ZGF and C check are the same. I mean, at least at the same notation.
Okay. Sorry, I think this is a typo. I should have flipped this sequence. So this here, this is C, and this is C check.
Okay.
That's a typo. Thanks, Yinan.
The order is not correct. Okay.
Thank you for pointing that out. Right. Okay. So the correct details are in the paper. The slides are prone to my errors. Okay. But yeah, if one does it correctly, as Yinan points out, then one gets the correct result. Okay, so this was the last example I wanted to talk about. And so let me conclude. So what did I talk about? So we considered supersymmetric quantum field theories, which are geometrically engineered in M theory. And we considered geometries whose boundaries contained ADE singularities. And then, motivated by orbifold homology, we gave a prescription in singular homology on how to compute the 0 form, 1 form, and 2 group symmetries of this supersymmetric quantum field theory. Now, in the papers, we cover more. So in the first paper, we systematically study the non-compact cycles of elliptic threefolds and also compute anomalies for 1 form symmetries via triple intersections in geometry. This is very interesting in itself and deserves its own talk. In the second paper, we also discuss G2 spaces. And the point here is that because we're only processing topological information, it's enough to describe these G2 spaces as uplifts of D6 brane configurations. And so for details, see here. Now, some outlook. This cutting and gluing procedure can, of course, be applied to global models. And so one slices up the compact geometry into non-compact parts and then asks how things like defects behave if I glue it back together and couple the local models to each other and to gravity. And this is something that we're thinking about. It's also very interesting, also an interesting point of view would be to study the symmetry TFTs from this slightly larger homology theory. So we would be considering differential orbifold homology and then compute anomalies for the structures we discussed today. And then finally, what's also interesting is that one way of phrasing what we did today is that we went to the boundary, and in the boundary we excised things. So we, in some sense, discussed the boundary of the boundary. And well, this iterates, of course, so we can keep going. If we have more complicated geometries, it might be worthwhile discussing the boundary of the boundary of the boundary. And in generally, these structures should capture n groups. Right, and I hope to tell you about these things sometime in the future. But for now, let me thank you for your attention.
Right,
Yeah.
Thank Max. Do we have questions? So maybe I can start with a question. Since you mentioned the triviality versus non-triviality of 2 groups. Is there a simple way to distinguish when it's non-trivial? Like, so think of this as a category. Is there a certain set of morphisms that's missing from the category? Is this the way to distinguish it?
So in the geometric setup, if the second short exact sequence that I flashed, if that splits, then the extension problem is trivial and there is no 2 group.
So I'm happy with this splitting argument, but I mean more like from the viewing the two group as a category.
Yeah.
Like let's say we compare two categories. One of them is a two group which is non-trivial. One of them is trivial. How do I distinguish? Is there certain sets of morphisms that's missing, or can I think of it in this way?
I mean, I'm sure you can think about it abstractly like that, but wouldn't know how to translate this into a geometric set.
Okay. All right. Okay, thank you. Antoine.
Yeah, I had a perhaps naive question, but I noticed that you always, so all your groups, you include the torsion. So you compute torsion of homologic groups. So are there many cases where this is useful, where you have actually a free part and you have to kill it? And if so, what's the physical meaning of that, of taking the torsion?
Sorry, say again. The physical meaning, there was some background noise. The physical meaning of the torsion parts.
Why you take the torsion part and why don't you keep the whole homology groups?
So intuitively, torsion arises like this. So we want to study line operators, well, extended operators modulo screening. And so as soon as we have an extended operator, and let's talk about lines, as soon as we have a line operator which we can end on a local operator, it's going to be screened and it's not going to be part of this defect data. And so how this maps to geometry is that if we have a torsion cycle, let's say if we say we have a torsion n cycle, then this means that there exists some cycle in one dimension higher whose boundary is n copies of that torsion cycle. And then wrapping an M2 brane on that, we can construct a local operator which ends the line. So in this sense, ending line operators and these local operators is very natural in naturally phrased in terms of torsion. Now,
I thought this was already captured by this relative homology groups, this effect of screening. And my understanding was that this torsion is just to kill some potential free parts. So these are abelian groups and they contain a torsion part and then potentially some free infinite parts. So does this happen?
So there are examples. So in little string theories, the thing you would compute has some free factors, and that has interpretation, which I don't quite.
Yeah, so I guess that's my question. What's the interpretation of those free factors, and why do you decide to kill them?
So in all the examples, they actually do not need to be killed that I discussed today. And there's a paper by Michele and Cantaro where they discuss this in detail. But I would have to look up the details to get back to you on that. There is no sound.
Sorry, I muted myself. So in all the examples of today, you could have removed this torsion thing. You could have just considered the relative homology groups.
Yeah, right. So there is. Okay. One needs to be a bit more careful. One needs to also see what maps into what, and yeah. But yes, I could have removed it.
Okay, thank you.
So you mentioned 7-dimensional theories with E-type gate symmetry.
So yes, they can be. So this would fall into the class of the first set of examples that were discussed.
Do you have an interpolation between M theory and type 2A, or is just in M theory?
Just in M theory. So this is there is. I do not know what the type 2A dual is of an E-type singularity.
I see. Yeah, but you do have for A and D.
Yeah, I mean, so for A, they're going to descend to D6 planes, and for D, it's going to be D6 planes plus orientafolds.
And for E, only in M theory.
Yeah, and for E, only in M theory.
Yeah. Okay. Yeah.
Okay. Thanks for the question.
So since you mentioned the TN theory, there's one thing that I'm still confused about all over. So this, and not just to you, but in general, a question I have. But since you mentioned the exact shape of the flavor symmetry, So there is, of course, also the idea of, let's say, exchanging the factors, the SUN factors.
Yes.
And when, for example, a brain web, then this is really a symmetry of the system if you choose tau right.
Sure. I would assume that Tn has an S3 symmetric group symmetry.
Exactly. Yeah. So this should still be part of a flavor symmetry, no? Or so would you add this to the SUN cubed mod Zn squared?
I see. So it could be added. So this is probably also one of these. Okay. If there are isometries like this of the geometry, that's something we also do not pick up directly with these topological methods, because right there isometry contains the word metric. So this is data we've thrown away. But something we can see, right, is that the center which was computed in the example is invariant under the transformation you just described. So yes, it would be compatible to add
the
S3 symmetry.
Okay, fair enough. That's I'm happy.
Okay, good.
So in a way, you're computing some kind of inner symmetries, and you don't see some kind of outer symmetry.
Exactly. So it's tied up. So okay, basically we are computing the symmetries associated with ADE loci and then correcting these. There could be enhancements, as in the E6 Niemann-Hamilton. There could be some isometries, as Julius just pointed out. These things are not directly captured by the formalism here, but they are compatible with it.
Mm. All right. Do we have more questions? Maybe if we have no pressing questions right now, then let's thank Max again. Start the recording.